You are welcome to my YouTube channel. Our topic for today is continued fraction. Let's begin with our definition. A continued fraction is an expression of the form a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus ... where a0 is an integer and a1, a2, a3 are positive integers. The notation for a continued fraction is a0 semicolon a1, a2, a3 ... Let's take some examples. Express q equal to 225 over 157 as a continued fraction. Solution: we have 21 over 5 to mean 4 plus 1 over 5, 68 over 21 to be equal to 3 plus 1 over 4 plus 1 over 5, 157 over 68 to be equal to 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, then 225 over 157 will be equal to 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. These expressions are called continued fractions. Theorem. Let's look at the existence and uniqueness of continued fraction. Let a and b be positive integers. Then, there is a unique way of writing a over b as a finite continued fraction, such that a over b will be equal to finite continued fractions, C0, C1, C2, down to Cn. The proof of this theorem is left as an easy exercise. Proposition: let q equal to a over b be a rational number greater than 1 in its lowest terms, so that the GCD of a and b is equal to 1, then q can be written as a continued fraction for some positive integers a0 down to an, where an is always greater than 1. The proof of this proposition is also left as an easy exercise. Let's look at this example. Compute the continued fraction of q equal to 87 over 38 without explicitly running the Euclidean algorithm. Solution: a0 is equal to 87 over 38, a0 will be 2, a1 will be 3, a2 will be 2, a3 and q3 will be 5. q1 will be 38 over 11, q2 will be 11 over 5, and q3 will be 5 over 1. Therefore, 87 over 38 is equal to 2, 3, 2, 5. Let's look at another example. Find p over q if p over q is 0, 2, 3, 4, 2. Solution: all we have to do here is to simplify the fraction. Now, 0, 2, 3, 4, 2 can be written as 0 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 2. And when you simplify further, at the end, you're going to get 29 over 67. Therefore, our P is 29, while our Q is 67. We want to compare continued fraction with Euclidean algorithm. Using the Euclidean algorithm, we compute the greatest common divisor GCD and derive the continued fraction expansion. 720, assuming we want to find the GCD of 720 and 164, the answer actually is 4 using the Euclidean algorithm. You start with 720, you express 720 equal to 4 times 164 plus 64, then 164 will be equal to 2 times 64 plus 36, and it will keep reducing down to 8, which is equal to 2 times 4. Therefore, the GCD is of 720 and 164 is equal to 4. We obtain that 720 over 164 can be written in continued fraction as 42132. Application of continued fraction in solving linear congruences. This proposition will be of help to us. Proposition: consider the case AX equal to B mod M and AM equal to 1. Thus, the solution of the congruent will be X equal to minus 1 raised to the power N, B sub N minus 1, and B modulo M. The proof of this proposition is also left as an easy exercise. Let's take an example to demonstrate the proposition. Solve the congruent. 256x is equal to 179 modulo 337. Solution: we have that the GCD of 256 and 337 is 1. Therefore, the congruence possesses a unique solution. Let us expand the fraction 337 over 256 into continued 1 as follows. By the time you break down 337 over 256, you are going to discover that your Q1 will be 1, Q2 will be 3, Q3 will be 6, Q4 will be 4, and Q5 will be 3. Now, you pick those values and use it to populate our table, and the table will look like this. You have I ranging from 0, 1, 2, 3, 4, and 5. Then we have our Q1, which is 1, 3, 6, 4, 3. Then we also have our P1 and Pi and Qi, which you are going to compute. Now, for this particular example, the way we computed our Q2 is 3 times 1 plus 0 equal to 3. Then our Q3 is 6 times 3 plus 1 equal to 19. Then our Q4 is 4 times 19 plus 3 equal to 79. While our Q5 is 3 times 79 plus 19 equal to 256. Now, for the values of the PIs, our P2 is 3, we got it from 3 times 1 plus 1, giving us 4. P3, we got it from 6 times 4 plus 1, equal to 25. Then P4, we got it from 4 times 25 plus 4, equal to 104. Then P5, we got it from 3 times 104 plus 25 equal to 337. It follows from the obtained data above that our n is 5, P sub n minus 1, which is P4, is equal to 104, and our B is 179. So when you substitute these values into the proposition, you're going to discover that S will be equal to minus 1 raised to the power 5 times 104 times 179 modulo 337. Thus, when you simplify further, you're going to have 55 plus 81 over 337. Hence, the solution is x equal to minus 81 mod 337. But since we want the smallest positive solution, our final answer is going to be x equal to 256 modulo 337. Now, we are going to look at the application of continued traction in solving problems on linear Diophantine equation. The steps are very simple. You see, especially step 4, which says from an bn minus 1 minus an minus 1 bn equal to minus 1 raised to the power n minus 1. That is the formula we will need in finding solution to linear Diophantine equations. Let's take some examples to see how this can be applied. Example: compute all convergence for the number 151 over 13 and solve the Diophantine equation 151x plus 13y equal to 1. Solution: the number 151 over 13 can be written as the chain of partial quotients, which is 151 over 13 will be equal to 11, 1, 1, 1, 1, 2. Now we'll construct the table of values for this particular problem. We'll have our I from 0 to 6. We have our small QIs 11, 1, 1, 1, 2. We have our PIs and QIs, just like the way we computed for the previous example. That's how we populated it. Now, by the property of continued traction, that proposition is going to help us. When you apply that properly, you're going to have that the solution to the Diophantine equation will be x equal to 5 and y equal to minus 58. Finite continued traction. Now, here, so we should assume A0, A1 are positive real numbers, and for n ranging from 0 to m, the nth convergence of the continued fraction is Cn. This convergence for n less than m are also called partial convergence. Let's see some examples on how to apply the partial convergence. This example says solve the linear Diophantine equation 474x minus 151y equal to 1. Always notice something here, that the GCD of the problems given is usually 1. In that case, you can apply the continued fraction. Otherwise, the continued fraction may fail. Solution: the continued fraction expansion of 474 over 151 is 3754. However, the second to last convergent is 375, which will give us 113 over 36. Since n equal to 3 is odd, we take x equal to 36 and y equal to 113 as a solution based on the proposition we just read. Now, verifying, we discover that when you replace x with 36 and y with 113, you are going to get 1. Thus, x is 36 and y is 113, and that is the solution to the equation. Let's look at another very important example. Solve the linear Diophantine equation 113x minus 36y equal to 1. Solution: the continued fraction expansion of 113 over 36 is 375. The second to last convergent is 37, which will give us 22 over 7. Since n is equal to 2 is even, x is equal to 7 and y is equal to 22 should be a solution to the linear Diophantine equation, with right hand side being minus 1. Verifying: if we make our x to be 7 and our y to be 22, we are going to get minus 1, but that is not the question. The question says we should get 1. Therefore, you move a step further. To obtain a solution for 113x minus 36 to give us 1, we modify the continued fraction expansion. From 375, we modify it to 3741. The second to last convergent now is 37374, which will now give us 91 over 29. Thus, x equal to 29 and y equal to 91 is a solution to the Diophantine equation. Thank you for watching.